to know if it's there or not. So to do that, you would shine some light at it. It would evolve differently depending on whether the object is there, and then you measure the light that bounces back and work out if the object's there or not. It's the kind of scenario we can describe with this basic setup here. We also look at multi-copy channel discrimination, which is a special case of this, where your channels are acting on multiple copies of the input all at once. So they're sort of acting on a bigger space, and your input probe state is of the form of a tensor product of the same state. So in all these channel discrimination scenarios, what we care about is the success probability of correctly guessing which channel was chosen. So here this will be, this is the success probability of guessing between some ensemble of channels using eta as an input state. And this is given in the usual way as the trace of the output against some measurement, and then we take the supremum over all measurements. So we assume that in this sense we can do the best possible measurement at the end.
Sorry, this notation, what does PI mean?
PI is so these are your possible channels and they're chosen with this probability.
Okay, just here.
Yeah. So we care about optimizing the success probability, so we have the best chance of guessing which channel was applied, and we do this by choosing the input state eta in our scenario. So our result is that for any resource state in an arbitrary resource theory, we can always find a task such that your resource state outperforms all free states. So specifically what we say here is that given a resource state, so any state outside of your free states, we can always find two channels that we're picking between, such that our success probability, when we use that resource state, two copies of that resource state as our probe state, is strictly better than using two copies of our free state, even in the best case scenario for free states here. So I'll go a bit into how we show this result. If we have two channels that are picked with equal probability, then we know that the success probability picking between them with some arbitrary input state eta is given by this formula here, this essentially trace distance between your two possible channels. This is from Hellstrom and Hinella many years ago. So essentially we can pick two channels and we can put them in this and calculate it. So the channels that we pick are these ones here. Essentially a projection onto 0 and 1, just some orthogonal base vectors with some coefficients that depend on your input state eta and also some operator x that I'll get to in a bit. And these channels don't really have any physical meaning. They're picked for mathematical convenience, essentially, so that basically the terms cancel out. So if we then put this into our formula for success probability, we get this output here, which depends just on the trace of your x operator that I'll get to and eta your input state. So our aim is then to just pick x such that it treats this success probability different for our resource state than for a free state. So in doing that, we'll create two channels that we're picking between that our resource state is better at differentiating between. The way we do this is through witness operators. So this is just some operator that separates your state from your free states, in the sense that if you take the expectation value of your witness on your resource state, it will be negative, and if you take it on any free state, it will be positive. So provided your free set is convex, we can always say that a witness, an operator of this form exists, thanks to a nice handy math theorem. And it essentially acts as a straight line. You can think of it as a straight line cutting off your resource state from your free states, like in this picture. The issue then comes in that we want our free states to be non-convex, and you can see here that we can't necessarily separate any resource state from our free states with just a straight line anymore. So we need a slightly different type of witness. Specifically, we need some sort of curve in our line, and the way we do that is we take a witness that acts on multiple copies of your state. So we can always find an operator like that. For example, this one here. The details aren't particularly important, but essentially we take this swap operator, which ends up giving us powers of a state when we put in multiple copies. So the details aren't really important. It just matters that one exists. So we then know that there is some operator where we take its expectation value on 2 copies of our resource state and it's negative, or we take it on 2 copies of a free state and it will be positive. So this is exactly what we're looking for, trying to separate row from our free states to put into the channels. So we then take this 2 copy witness, we define this x in this way, and then we simply put this. The inequalities of it being a witness translate in this way. We get its expectation value on 2 copies of row is now greater than 1, and on 2 copies of a free state will be between 0 and 1. So we take our channels from before and we put x as an operator in here, and then the success probability we get at the end is now different depending on whether we're using row, our resource state, or any free state. So we now get a greater success probability for using row in this task, specifically differentiating between these 2 channels. So that's the result we have.
So Leah, sorry,
Yeah.
which sort of physical channel would that be?
So physically, I can't give it much meaning. It's very much a mathematical proof of existence, really. Something we'd like to look at in the future is whether we can do this with some actual useful channels.
Okay, so you don't have a proof that that you have that the subject would win anyway for anything for a given physical channel, right?
No, we don't have. No, it's a result that's the channels we construct are based on the state we're using. I'm not saying that the state is some magical thing that will work in all these settings. It's just a specific one. Yeah. Yeah, so the second part is looking at quantifying this advantage and how we can say how useful a state is in these sort of tasks. To do this, we look at resource monotones. So the intuition here is that a state that's more resourceful will be more useful. And this makes sense, but we need a formal way of saying what I mean by more resourceful. So to do that, we use resource monotones, which are just functions that quantify the amount of resource in a state. So you take your state, put it into this function, and you'll get some value that tells you how resourceful it is. In order to give this some meaning, we put some restrictions on this because there's so many ways of defining functions that will give you some number. So we say that these functions have to be faithful, which means that any free state will be classified as having no resource, and any resource state will be classified as having some amount of resource. And we also say that these functions can't increase under your free operations, so that easy operations you're allowed to do can't increase the resource. For example, if we go back to entanglement, you have a state and you do some local operation that shouldn't increase the amount of entanglement in your state. And then the other restriction we have is that we want these functions to have some meaning. So we want to be able to take the number we get at the end and to interpret it in some sort of setting that we're interested in. And there'll be different monotones will work with different settings. Specifically, what we look at is called generalized robustness, which is defined in this way. It's defined as taking your state row and mixing it with some other state tau. We increase the amount that you're mixing it with until your overall state becomes free. Yeah. And this kind of tells you how useful a resource state can be in channel discrimination. And this link has been found in lots of different cases before. Firstly, assuming that our free states were convex, and we were looking at discrete variable theories, so working with finite dimensional Hilbert spaces, and then extended in many ways. And our work here extends it to non-convex free sets and continuous variable theories, which is where non-Gaussianity as a resource lies. So if we look at robustness and non-Gaussianity, we're just saying how much we can mix our non-Gaussian state with some other state before it becomes Gaussian, before all our resources are lost. Now, this is quite a good measure for quantifying non-Gaussianity for 3 reasons. First of all, it's faithful, which means that all your Gaussian states are quantified as 0, and all your non-Gaussian states have some positive amount of non-Gaussianity. Second reason is that if we take our state and we apply some Gaussian operation, so some easy operation to do in our setting, this doesn't increase the amount of robustness, it doesn't increase our non-Gaussianity. And then the third reason is a mathematical technicality, and it's a lower semi-continuous function, which essentially means if you perturb your state slightly, you don't drastically increase the resource. So it sort of prevents easily creating non-Gaussianity. So we can calculate this robustness for some examples. Firstly, we have Fock states. So if we take a single particle state and we calculate this, first of all, we have some equality for pure states, which is given by an infimum over all Gaussian states. So we can put any state in here and it will give us an upper bound. Then we also use the link between robustness and relative entropies. Robustness is actually given by max relative entropy exponentiated, -1. So we use this link in order to make a lower bound by instead just putting in the usual relative entropy, which we know how to calculate. So in this case, we can put some states in and we find that the robustness of the Fock state is given by this formula here. And so the robustness increases linearly with your photon number. You can also look at a second example here, so a mixture of coherent states. So this is a mixture of 2 states that themselves would be Gaussian. So this overall state wouldn't be considered useful for a lot of scenarios. So this is just a vacuum that's been displaced by D in one direction and minus D in the other direction, and then we mix it together. So in our framework, these states are seen as resourceful because they're not Gaussian, even though they're not typically considered too useful in general applications. And again, we use the link between robustness and relative entropies, and we can find some lower bounds in the state. So essentially, even though this state wouldn't be typically considered very useful, its robustness is still at least this function here that increases with the separation distance. You can also interpret robustness now into this channel discrimination setting that I talked about earlier. We can give it 2 interpretations. The first is a worst case interpretation. So we say that our robustness exactly gives us the worst case advantage in single copy channel discrimination. So our 2 channels we're picking between and our input state is just 1 copy of the state. And specifically the success probability of picking between 2 channels using your resource state as an input state versus using some Gaussian state is given by the robustness here. And this can be interpreted as saying that if for any non-Gaussian state, if you were to then give me some Gaussian state, I could always find some channel discrimination task where your non-Gaussian state outperforms your Gaussian state. And it'll outperform it by at least this amount, 1 plus your robustness of the state. We can do this for any non-Gaussian state. And then the second interpretation is in terms of multi-copy channel discrimination. So we're looking now at input states that are of the form of multiple copies of your state. And in this case, we can still use robustness to upper bound the advantage you get in this scenario. And now we're looking at your non-Gaussian state compared to all Gaussian states. So the best you can do with a Gaussian state, you'll still be able to do better with your non-Gaussian state in some task. Yeah, so that's the end. A quick summary is that for any resource state and any resource theory, you'll always be able to find some channel discrimination task where it outperforms your free states. We only need 2 copies of the states to show this advantage, and that works in arbitrary resource theory. And we can link this advantage to general to interpret a single copy and multi-copy setting. Thank you.
Thank you, Leah. Questions?
Yeah, so one question. You mentioned a link between the robustness and the mass relative entropy at some point, right?
Yes.
We have like an operation where we could interpret what mass relative entropy represents in this context, because it's associated with single copy, not like non-asymptotic entropic quantities, usually. I don't know if in this context, is there a simple way to mean what it means?
In this context, well, it's still, it's a good question. It's still interpretation in terms of sort of your usual hypothesis testing. It's a similar thing, really. Hypothesis testing and state discrimination and channel discrimination that still. In this setting, I'm not sure how exactly it would. How to give you a nice way of thinking about it in terms of this, I'm afraid.
Any other question? What is the relation with quantum hypothesis testing? So if I try and estimate the bound scenario, the F bound that stems from symmetric or asymmetric, I don't remember which one of them. I do quantum hypothesis testing. Do you know if similar results can take place in that context as well?
Well, I'm sure you could do. I'm not sure of exact results, but I mean, we're looking here at discriminating, essentially state discrimination between your potential output states, applying one channel and another channel. And then, obviously, hypothesis testing, you're looking at a limit of infinitely many states.
Yeah.
I don't know how taking a limit here would apply, but I believe it's been looked at in some cases, yeah.
Okay. So if not, then we move to quantum technology.